Okay, so the linear equations that we're going to talk about. We're going to talk about, first off, an equation. An equation is a statement that equates two expressions. That's almost like a self-referential definition, right? But an equation is different than the expressions that we were talking about on Wednesday in the sense that it has this equal sign that says this expression is equal to this expression. Now, one of the expressions may be utterly simple. It may be something like a zero or something like that, or they may be more complicated mathematical expressions. But the essential part of an equation is that it has the equal sign in it. So we talk about linear equations, and we're going to talk about linear equations in one variable today. It's an equation that we can write in this form, where we have ax plus b equals 0. And in this case, we don't want a to be 0, because if a is 0, we don't really have an equation. We have b equals 0, right? And so the funny notation after that a does not equal 0 is just that a and b, and what that funny looking e stands for is an element, and then that funny looking r means the set of real numbers. So it means that a and b are real numbers. In this course, we're not going to talk about complex or imaginary numbers. The square root of -1 is just not going to exist in our book. So we're looking at the standard form as ax plus b equals 0. Obviously, you can start in a non-standard form where you have what looks like a more complicated expression. But any equation that can be reduced down to this is a linear equation in one variable. So when we talk about solving an equation, and this applies to any equation, not just linear equations, it means that we're finding all the values of x that make the statement true. So you have an equation, there's a variable in it. We're going to look at the generic x, but it can be any variable. And the solution to that is finding all those values that make it true. So now we may get different results when we solve it. We may get something that says all numbers make the statement true. So whatever value we put in for x, it's still a true statement. And we call that an identity. So when the solution set is all real numbers, we have an identity. That means that that equation that we have is true under all circumstances. Now, if we only have some real numbers, not all real numbers, but some numbers, maybe one, maybe more, form the solution, we call this a conditional equation. That means that there exists a condition where x has to be a certain value for it to be true. Now, with linear equations, it's true that we're only going to have either one solution, or all numbers are a solution, or there's going to be no solution. We're never going to have a linear equation that's going to have two solutions. We're going to look to quadratic equations for those, and that comes later this semester. So if nothing makes it true, when it's no solution, we call it a contradiction, okay, where there's no value of x that you can put in to make something true, so that equal sign is obviously wrong in that sense. And so that's where the sense of the contradiction comes from, is that we have something that can't be true. So you're making a statement involving x that contradicts itself in some fashion. So the first thing we got to do is learn how to test to see if we have a solution. So if we have this equation, this 5x plus 9 equals 4, that's not in standard form. Why is it not in standard form?
It's not equal to 0.
Excuse me?
It's not equal to 0.
Yeah, it doesn't equal 0. So it's a linear equation, but it's not in standard form. And it's perfectly fine. It's a sound equation, but it's not in standard form. Okay, so is this a solution? Well, the way we figure this out is that we place the candidate solution, x equals 2, in where the the equation declares x to be, and so we have 5 times 2 plus 9 equals 4, and we get 10 plus 9 equals 4. That's not true, so we have a contradiction, or not a contradiction there. What we have is x equals 2 is not a solution, so it's that simple of a statement. Okay, so is x minus 1 a solution? Well, we just pop it in and we say, okay, negative 1 times 5 equals negative 5 plus 9 equals 4, and 4 equals 4, so we have a solution here. So that is the solution. Now notice how I did this, and I think mechanically you should get in the habit of doing this. I think I expressed this on Wednesday as well. I didn't just write 5 times 2. I wrote a parentheses and I put my x value in the parentheses. And the reason why I did that, it's probably not so important on that first one, but on the second one with the negative 1, I'm retaining two things. I'm retaining number 1, that I'm multiplying. Number 2, I'm retaining that it's a negative 1. So there's no ambiguity with the notation there. It's clearly 5 times negative 1. And so when you're trying out solutions or plugging in numbers and things like that, these parentheses I think are really vital, because you've made 2 steps then. The first one is the step of just plugging in the number. Then the second step is then evaluating those expressions to see if you get what you're looking for. And so there again, writing a little bit more actually is a little bit more reliable than not writing and doing things in your head. I mean, certainly you can test that out in your head. This is perhaps a simple enough one where we can think, well, if x equals negative 1, and then essentially do that computation in our head. With more complex expressions, it helps to have it written down. So let's get into the habit early on with simpler problems to make all the notation work, on our behalf, that we don't have errors in the sign or anything like that. Okay, so we have this notion of forming equivalent equations. Now, I think you've all done this, where you have an equation and you want to transform it so you can solve for x. And so what you do is you add things or multiply things to both sides and all that. You really are changing the equation. What we're doing is we're following those properties of real numbers and expressions to form equivalent equations. And so that's why we went over all those properties, is because those are the legal operations that you can do. And so with linear equations, it really comes down to maybe these few steps where we can simplify either side. So we're not touching both sides. We can simplify both sides, but we're not making the sides relate to each other. We're just taking this thing of 4x minus x, and here we have 2 terms that are similar, right? They both involve the variable x. Different coefficients, 4 and negative 1 are the coefficients, so we add those and we get 3. So we're just simplifying this. This is an equivalent equation. It's not the same thing, but it is equivalent. And what we mean by equivalent then is that it will have the same solution as the equation that we started with. So when we make this simplification, we haven't changed the meaning at all of what x is or the possible values of x, but we've made an expression that is perhaps a little easier for us to continue to solve. The other thing that we can do is we can add something to both sides. And by adding, I'm also meaning subtracting, right? Where you can either add or subtract the same number to both sides. And with addition and subtraction, you don't have to worry. There are no rules that you have to avoid. You can certainly add 0 to both sides. You won't change anything. You can add 1 or any negative number. So addition and subtraction always work. And so here's the example. If you have an expression, x minus 5 equals 2, we're going to add 5 to both sides and we get x equals 7. Now we can multiply both sides. And so in this case, I'm going to multiply both sides by 1/3. And we get 1/3 times 3x equals x, and then 1/3 times 12 equals 4. This is kind of like dividing, right? This is essentially dividing. We're dividing both sides by 3. So there's that equivalence between multiplication and division. The one thing that we can't do with this is multiply both sides by 0, because then everything evaporates, right? If we're trying to find a solution, there's nothing productive that we do with multiplying both sides by 0. So if we multiply both sides by 0, we get 0 equals 0, which really doesn't tell us anything. So it's, in that sense, not an equivalent equation because it doesn't have the same solution set. And of course, division, we can't divide by 0 because we have an operation that just doesn't work. That doesn't advance our understanding of the equation. It doesn't give us an equation that has the same solution. We just don't divide by 0. The other thing that we can do is interchange the sides. If 12 equals x, then x equals 12. Now, you'll do this for two reasons. Number one is there's times where either the left or the right is the more complicated expression, and just the way you format your paper, you want to start out and have all your equal signs one under the other and make it nice and neat. So you can take the shorter one and put it on the left and the longer one on the right, and then you don't have to worry about, estimating where you have to start in writing. So it's useful in that regard. It really doesn't change anything meaningful in mathematics, so you can feel free to do it. The other thing is at the end, when you're finding the solution, it's kind of like Yoda speak when you say, okay, find x, and you say 12 equals x. Well, what you really are trying to say is x equals 12, right? So with an equality, it works where you can flip things around like this, and so oftentimes the answer is let's say, more nicely presented as x equals 12, even though the meaning of 12 equals x is identical to that. So this is not a big deal, and it's something that we probably do without thinking about it, but formally in mathematics you can do this. Okay, so let's look at an equation in standard form now. So we don't know what values of x make this thing true. Now, we can probably be clever and figure it out in our head, but to do this thing using those 4 rules that I had before, the first thing we want to do is we want to subtract 15 from both sides. And so once we do that, then we simplify both expressions, and the 15s drop away on the left side, and we have a negative 15 left on the right side. So we combine those terms. And then we're going to divide both sides by 3. And there again, we're going to simplify again, and we get x equals negative 5. So we can check. And so we use that device again where we put a parentheses where the variable was. We drop in our negative 5. We say 3 times negative 5 is negative 15. Add 15 to it, and you get 0. Now, if I explicitly ask you to check, I want to see that you check something. But in general, I'm not going to ask that you check your solutions. But I think it's a good idea to do this. It's always a good idea to check your math. I said earlier, if you just go over all your steps and say, did I treat my signs correctly? That's a good first question. If you have something like this that substitutes relatively quickly, this is kind of the proof is in the pudding here, that negative 5 does work in this equation. It does make it true. So that's easier than looking at every step for the sign. So if you get something that's not true when you check, then the first thing to check, I think, is did you mess up on one of the signs? Chances are that's where it is. It's just one of those things that it's an easy mistake to make. And so even though you understand it perfectly, everybody makes these little mistakes. So that's the first thing to check. So I guess the point here also is that when you're checking, you have to go back to the original equation. It's true that you can use any of the intermediate equations to see if that works, okay, and that might be a way to diagnose where you've gone wrong if something doesn't work out. But the real proof is you go back to the original problem, the original statement. So if it's not in standard form, don't first put it in standard form and then check it. Check it just the way it is. That'll tell you, did you make a mistake or not? Because if you've made a mistake in putting it in standard form, then checking doesn't really help you very much. Okay, so you try this one. That's 7x minus 12 equals 0. Sorry, my writing got a little small right there. I'm going to send around a sign-in pad, if you would sign it. If you are not officially enrolled, please go see Professor Hammacher and get yourself involved with his process. There's nothing I can do or nothing I should do with an add and drop slip. That's all done centrally in the math department by Professor Hammacher. Okay, got a solution? What is the solution? 12 sevenths. Okay, add 12 to both sides. Simplify, divide both sides by 7. And so leave it as a reduced improper ratio. What that means is that if you had something like 12 sixths, you would reduce that to 2, of course. Or if you had something like 9 sixths, you would reduce that to 3 halves. So you would reduce it, take out the common factors, but don't make it a mixed fraction, okay? Leave it as this, because algebraically, this is the most useful form that you have. Chances are when you're doing some calculation that your calculation is made up of a whole bunch of intermediate steps, and you might have little problems along the way to get to a goal. There's nothing better than a reduced improper fraction because you can use it directly and it's exact. So if you make this as x equals 1 5/7, that's not too bad. It's not great because if you have something like 2 5/7, if we're dealing with algebra, does that mean 2 times 5/7, or does that mean 2 plus 5/7, which is what a mixed fraction is? So to avoid that kind of ambiguity, that you've fully completed something, leave it as an improper fraction. But please, please, please don't do this. This is terrible, okay? This does not equal 1.714. Well, it's only approximately that. And certainly there's ways of notating repeating decimals and all that kind of stuff. But whenever you write it, you do some rounding. And so probably all the science faculty will tell me this is not so terrible because that's the solution that they're looking for. You want a number that you can measure, or a number that you can communicate, and so you do put things in decimal numbers. And so it's not the end of the world if you do it, but from an accuracy standpoint, you're much better off with the ratios because there's no doubt you're not ever rounding to an integer, right? Something like 12 sevenths is exactly 12 sevenths. You didn't round that from 12 over 7.1. Since you're using integers, you can pretty much infer that you've gotten there from an integer. But with a ratio, you think, or with that decimal, is that exactly 1.714? Is that rounded? Is it rounded properly? There's even different rounding rules that people use. A bank rounds numbers differently than a scientist. Your computer probably rounds in a way that you don't really even think about, where it alternates rounding up and down from a 5 and that sort of thing. So we're just not going to talk about rounding rules here, and we're just not going to deal with rounding. We're going to keep with integer ratios. Okay, so here's another one for you to try. Now this one is a little different because it's not in standard form. And here we're solving for y instead of x. Okay, anybody get a solution? 2 is the consensus solution? Okay, so I want to give you a little tip here, and perhaps I should have done this before you started. But when you have something like this, it doesn't really matter which side you end up with containing the variable and which side will contain the constant. And so one of the easiest things that, or one of the ways that you can make your life a little easier in this is inspect the equation and decide which side of the equation will you end up with a positive coefficient for your variable. And in this case, it's going to be the right side, right? Because 12 is greater than 9. So you probably went through a process similar to this, where you either dealt with the variable term or the constant term first, but if you did this, you subtracted 9y from both sides, simplified that, and then you added 2 to both sides, and simplified that, you get 6 equals 3y, divide both sides by 3, and there you are, 2 equals y, or y equals 2. And so we can check this again. We put it in the original expression. Boy, I really did get tiny writing on there, didn't I? So this is 9 times 2 plus 4 equals 12 times 2 minus 2. And so 22 equals 22, and we're good there. Now, occasionally we'll get linear equations with fractions. And so there's a couple ways to handle fractions. You can make the common denominator. You can eliminate the fraction. And I think the easiest way is to eliminate the fraction. The common denominators ultimately will use the same numbers that we're going to use by eliminating the fractions, but you'll see you get an all-integer equation if you use this method. So the first thing we want to do is we want to find the lowest common denominator. This would be the least common multiple, I think is what I called it earlier. Basically, we want to factor what's in the denominators, inspect them to see what's in common, and so what we do is we take the unique factors times the common factor, and so the lowest common denominator here would be 30. So if you were to make these into fractions, you would make everything over 30, right? Now, you don't need to do that. All you need to do is multiply this lowest common denominator to both sides. And so we're going to say 30 times the expression on the left and 30 times the expression on the right. And as we use the distributive property of multiplication, we're going to get 30z plus 30 over 15 equals minus 90 over 10. And if you simplify those, we get 30z plus 2 equals negative 9. And so here we have our integers again. So we've eliminated them by essentially canceling out the denominator. And so by using this, what would be the common denominator, we actually transform this thing into an integer expression, or an expression or an equation with integer coefficients and only. And so from here we use the things that we've done before, where we have first subtract 2 from both sides, and we get 30z equals negative 11, z equals negative 11/30. Okay, everybody have that? So we'll check this, and with fractions it's a little bit more work, but it's worth doing. So we have 11/30 where the z was, and then we have plus 1/15 equals negative 30. And we already know what the common denominator is, so I can just make the transformation of those two other fractions by multiplying the 1/15 by 2 over 2 and the negative 3/10 by 3 over 3. And then ultimately I'll get negative 11/30 plus 2/30 equals negative 9/30, and lo and behold, we get negative 9/30 equals negative 9/30, and we're done. Okay, so we've checked that. Now we have a similar strategy for decimals, but first, why don't you try that one? Okay, use the method that I showed you of eliminating the fractions rather than finding the common denominator. Okay, what do you think? Still working on it? You want another minute? So what do you think? Did somebody get an answer? Yes. 24 over 7. Good. Okay, so let's see how we can do this. We find the lowest common denominator by factoring the 6 and the 8, and we discover we have a 2 in common. And so the lowest common denominator is that common 2, and then we have the unique factors 3, and then 2 times 2, so we get 24 as the lowest common denominator. And so we multiply both sides by 24. And so we get 24 over 6 and 24 over 8, and that is guaranteed to reduce. That's why we chose the LCD that we had, is because we knew that those things will go and make an integer ratio, and you don't even really have to do the division. You can do it by inspection. What are the factors in 24 that are not in 6? And you can see that we have a 2 times 2 that are in 24 that are not in 6, so you know that that one goes to 4. So if you've written out how you factor it, you don't have to do the division longhand, you just do it by inspection. You see which additional factors do you have. And so we get this equation then, 4t plus 3t equals 24. Combine like terms, 7t equals 24, t equals 24 over 7. Okay, so for decimals, we do something really similar, except that we're going to multiply through by 10, 100, 1,000, whatever it takes to eliminate the decimal number. And so we may get some rather large numbers there, but the good news is that they will be integers as well. So if we have something like 6.5 times 1 minus 2x equals 13, we look at where the decimals are, and we say, okay, well, there's only one number that has a decimal, and that's the 6.5. So we're going to multiply both sides by 10. And so I'm going to take 10 times the expression on the left and 10 times the 13 on the right. And here I'm going to make use of the associative property of multiplication. Here's a potential point of confusion. Do you multiply the 10 times the 6.5 and the 1 and the negative 2? Well, you're multiplying 3 factors, right? You treat the thing that's inside the parentheses as one factor. And so we can just change the order of multiplication, that instead of 6.5 times the 1 minus 2x, we're going to first change it to, say, 10 times 6.5. And so the first step that we have is 65 times 1 minus 2x equals 130. Yes?
Inside the 1 and 2, we don't like the 2, like 10 minus 28.
No, you don't multiply that in, because what you're going to be doing is actually multiplying by 10 twice then. Okay? So I'm making use of the fact that we have something like this, where this is multiplication between these two, right? So this is the same thing as then using the associative property, which says I can do this. Okay? This is not the same. Then I think what the temptation is to want to do is to multiply this out so you get that. And that's wrong, because you've multiplied it too many times. Now, the other way to do this, if you're uncomfortable with that, is that you can first multiply the 6.5 through, and then you have 2 terms, and then they all get multiplied that way. But then we're creating more decimal fractions that way. Okay, so what we're trying to do is eliminate the decimals as soon as possible. And since we have a factor, this could be and it is, in this case, an expression that's contained in a parentheses, and we treat that just as a factor. We don't multiply, if we wanted to multiply this A through here, then we don't multiply it by the B. Okay, and there would be the difference. So there's two ways that we can go from here. We can either divide both sides by 65 since we have factors. That's perhaps the easiest way. Or what we can do is we can expand the left and then solve the equation the way we have before, where we first subtract 65 from both sides. And then we have negative 130x equals 65, and so we divide both sides by negative 130 and we get negative 1/2. So a couple different routes, maybe 3 routes that we can take to get to this solution, but you should always get to the same solution where x equals negative 1/2. Now we can check this. I didn't actually write it all out, but we can probably do this one in our heads where we say negative 1/2 times negative 2 makes a positive 1. So we have 1 plus 1 is 2. So we have 2 times 6.5 equals 13, and that's true. So you can check that one mentally if you like. Okay, so here's one for you now. Try this. And what I'd like is, I'm going to ask somebody to do this one on the board once I've given you enough time, okay? So prepare it in a way that you can do it on the board. Did you get it okay? Do you want to do it? I think the red marker is the one that works the best up there. Okay, so you solved it without eliminating the decimals.
Yeah.
Which is fine, okay? And in this case, it works out fairly simply because you have this nice ratio of 12 over 1.2, and that gives you a 10. Now, if you were to do it by eliminating the decimal, you'd multiply both sides by 10. And then now you do the distribution because it's 10 times this quantity. And so we say 10 times 2.2 is 22x, 10 times negative 5 is negative 50, and then the other side is 10x plus 70, and then we add 50 to both sides. And then we simplify, subtract 10x from both sides. And we ultimately get 12x equals 120, which is 120. So in this case, fewer steps for you. That may work out? Yes.
Yeah. The only reason I did that was because I'm thinking that like later down the road, if we had like eighths, let's say like the decimal goes to the thousands place, you're going to be multiplying by 1,000.
Mm-hmm.
I just think that's just creating a lot more work and too big of numbers.
Yeah, and it is a matter of a judgment call. Which one do you end up with simpler numbers to deal with?
Right.
And so, when you have an integer solution like this, they all, regardless of the path, they all kind of work out nice and tidy. When you're doing, division by decimals, then if this didn't work out so tidy,
Yeah.
then you have to then multiply both the top and bottom by 10 to get something. So it's your choice. This is just a method of eliminating decimals if you don't like seeing decimals in equations, yes.
Can you also multiply by 10 at that third step? So you go to 1.2 times 10?
Sure, right here, you have 12 times, 12x times 120, which is what I have in my second to the last step.
Right.
So at any time you can do that,
Yeah.
okay? It's, depends on how many instances of decimals you have. If you have a whole bunch of numbers that have decimals in them, you might want to just eliminate all of them in one fell swoop. But I think on a simpler problem, you can make a reasonable argument that you can do it any other way. Just be comfortable with the methods, and it's certainly your shot. In most finding solutions to most algebraic equations, there's certainly more than one path to get there, but you get to the same place. Okay, so let's look at a couple other cases now. Let's look at this one. I'll give you just a minute to go ahead and, just so you see what happens on this, try getting it, then I'll show you my simplification of this and what we get out of it. Okay, I see a lot of you have kind of wrapped up a calculation, so let me go through one here. And so the first thing I would do is distribute the 3, and then subtract 6 from both sides, and we get 3x equals 3x plus 9. Subtract 3x from both sides, and we get 0 equals 9. Now this is not true, right? 0 does not equal 9. So this is a case, what would you call this?
No solution.
No solution. Perfectly good answer. The other statement you make about it? It's a contradiction, right. Okay, so then we have, like you said, no solution. Let's take one that is a similar looking equation. Look at this. The only thing that changes is instead of plus 1 in the right half of the parentheses, I put a negative 2. So work that one through and see what you get. All right, so we follow similar steps. First, simplify the right by extending that 3 over the x minus 2, and we get 3x minus 6 equals 3x minus 6. Right there is enough to recognize what you have here, that when you subtract 6 from both, or you add 6 to both sides, subtract 3x from both sides, you get 0 equals 0. And so, what does this mean? Infinitely many solutions. This is true for any value of x that you put in there. That first statement is true. You can try it out too. Let's say x equals 4. Okay, so in the first statement we have 3 times 4 is 12 minus 6 is 6. So 6 on the left side, and then we have 3 times 4 minus 2 the 4 minus 2 is 2, 3 times 2 is 6, so we have 6 equals 6. You try with any number and you'll get an identity like this. So we call that infinitely many solutions. We can say it's true for any value of x, and we can also call this an identity. And any of those three are interchangeable in terms of answering questions on a test or making a statement if you're doing work in any other sort of context. If you're in a lab or in a business situation, probably the first one is the one that is most clearly understood by the most people. You can say this equation is true for any x. Okay, that's plain English. To say it's an identity, you're really talking more in the language of math. So any of those three things work.
Can you do x equals and then the infinity sign?
No,
No.
because x does not equal infinity. Okay, when we talk about intervals, we can say that x is an element of negative infinity to positive infinity. But x equals infinity is, well, first of all, x is a number, equal says it's equal to something else. Infinity is not a number, it's a concept that says numbers increase without bounds, and so it would be a wrong statement.
Okay.
Okay, so here's one for you to try. Okay, I see most of you have finished. What's the solution?
Solution.
No solution?
Yeah.
Okay. Let's see how we get there. So first, we multiply the right side by 2 to expand that factor of 2 times 1/3 x minus 1. And then we see we have a fraction, multiply both sides by 3. And then we eliminate the fraction, so we have 2x plus 12 equals 2x minus 6. And at this point, this is sufficient. You can do that by inspection. You say, well, clearly, if you subtract 2x from both of those sides, you get 12 equals negative 6, which is a contradiction. But if you want to, extend that out, you get to that point, you call this a contradiction, or you say no solution. And then one last one here, one that looks similar in some respects.
equals 0.
0 equals 0. So what does that mean?
Infinitely many solutions.
Great, okay. So probably did something like this. So there's kind of a theme developing here. First, we expand the parentheses. So we have just the sum of terms on both sides. Then we simplify both sides, and then we start subtracting things from both sides. And in this case, I've subtracted 5 from both sides. You get 40 equals 40. If I subtract 40 from that, I get 0 equals 0, but we can stop here anytime we have an identity like this. And so we do have infinitely many solutions. And that's it.